In this video, we're going to go through IR spectroscopy. I'm going to approach this a little bit differently than I did in the lecture notes. I'm not going to focus a terrible amount on the theory. I'm going to go through what an IR spectrum, as what you can see here, means, and then how we can use it to deduce molecular structure. All right, so here's an IR spectrum. You're going to actually use this technique in lab. You can see on the x-axis you have what are known as wave numbers. This is going to be the frequency. Okay. And then on the y-axis we have what's called percent transmittance. So this is going to be how much IR frequency is transmitted. So if we look, 100% transmittance means that there is no absorption, whereas 0% transmittance means we have max absorption. Okay. We know from our discussion of general chemistry and chapter 1 that electrons occupy quantized energy levels. Bonds are shared electrons. If we irradiate a bond with electromagnetic radiation, we can cause the electrons to move. If we hit it with the right amount of radiation, we can excite the electrons to a quantized energy level. Or we can take the electrons and have them vibrate so that they absorb a certain amount of frequency. That frequency or energy that's absorbed is going to depend upon the atoms that are attached to the bond and the type of bond present. So, how much energy is absorbed depends on the atoms attached to the bond and the bond type. Is it a single? Is it a double? Is it a triple bond? Okay, and so what we're doing in IR spectroscopy, we're using infrared radiation, and we are trying to make the electrons in the bond vibrate. And we are trying to make them vibrate so that you can absorb the frequency. So we have to hit it with that right amount of energy. So if you remember, frequency and energy are directly related. Okay. So what we're trying to do again is we're trying to see how much energy a particular type of bond can absorb. And then we look to see that absorption in the spectrum. So I've taken this table from your textbook. You don't have to memorize this table, but you're going to use this table to help you interpret IR spectrum. You can see certain types of bonds. So here's an OH bond, absorbs a certain range of frequency. So if you look, if you have an alcohol OH group, it's going to absorb between 3,200 to 3,600 wave numbers. A carboxylic acid OH absorbs a little bit less frequency, between 2,500 and 3,000 wave numbers. So this is where you have to know your functional groups. So you memorize your functional groups, and then we take an IR spectrum of our compound, and we use this table to determine if that particular functional group is present, because each functional group is distinct in the type of IR frequency that it will absorb. All right, if this seems very abstract to you, let's work on some examples. At the top, I have a sampling of molecules. We're going to go through IR spectra for each of these molecules. And so I'll show you how it matches up and how we can get information about the functional groups that are present. So here I have my IR spectrum below. Again, on my x-axis, I have wave numbers. On my y-axis, I have percent transmittance. So let's label the peaks numerically, or signals, I should say. So here we have one that's around 3,300 wave numbers. Okay. Here I have one, looks like it could be about 2,950. And then this one here, let's just say is 2,800. And then here I have one around 1,500. So what we're going to do, let's also note, so I've noted the numbers. Now let's talk about the shape. Okay, if we look at the shape of the signal, we could say that this is very broad. It's broad. Here we have a sharper signal, and here we also have a sharp signal. Let's talk about the intensity. The closer we get to 0% transmittance or 100% absorption, the more intense the signal. So we would say that this is a very intense, strong signal. This is also an intense, strong signal. And here this would be a medium strength signal. Okay. The intensity of the signal has to do with the dipole moment, generally speaking. Okay. So the stronger the dipole moment, remember, that's that change in polarity where one atom is polar or electronegative and the other atom is not. The stronger the dipole moment, the more intense the signal. Okay. Now what we would do is we would go back to that table. So you have this table in your textbook, so you could pause the video here and go look at the table and see which types of bonds these values and my characterization of the signals correspond to. If you were to go back to that table, you would see that this corresponds to an OH. This most likely is a CH bond. All right, and here this one's hard. Okay, so typically in this region that is, I would say 1,400 or less. Right, that's the fingerprint region. And that is really going to give you a particular signal for a molecule, but it's very hard to identify peaks in there. So we don't typically identify peaks below 1,500 wave numbers. So let's look at our choices up top. Well, we can definitely rule out the alkane. We can rule out the alkene. All right, so we have an OH group. Could be that alcohol. Could be a carboxylic acid because it also has an OH group. We'll get back to that in a moment. It's not the NH2 because that OH signal is so strong and broad. And the ester doesn't have an OH group. All right, so now we have to decide between the alcohol and the carboxylic acid. We can rule out the carboxylic acid because there is no stretch for that carbonyl. You'll see this in other spectrum. You typically will have a very strong stretch between 1710 to 1680 wave numbers. It is a dead giveaway for having a carbonyl. So the only possibility would be this alcohol. Okay, so this is what you're going to do. You're going to do this on compounds that you isolate in lab. You're going to do this on unknowns, and you're going to do this in lecture. Now let's look at the second spectrum here. This is a new molecule. Let's just cross this one off our list because we already did it. We're going to do the same thing again. Let's label the peaks, or the signals, I should say. So this one here is around 3,000 wave numbers, and then here we have a signal right around 1,700 wave numbers, and you can see that it's split in two. And then we have this fingerprint region again here that we're not going to worry about. Let's look at the intensity and the shape. We can see that this is very broad and it's intense. And here we have a very narrow, sharp absorption that is intense. All right, so pause the video. I want you to go back to that table, and I want you to try and identify what bonds, what types of bonds these signals correspond to. So if you went back to your table, you should see that this broad, intense absorption at around 3,000 wave numbers corresponds to an OH bond for a carboxylic acid. It's very broad because of the extensive hydrogen bonding that carboxylic acids can do. They have greater hydrogen bonding than alcohols because you have an extra acceptor on the carbonyl of that carboxylic acid. Then we have a carbonyl. We have a C double bond O signal. It's very distinct. It's right in that right region. And as I said to you before, it's split in two. So that indicates we most likely have two carbonyls. All right. The only choice that would work would be this dicarboxylic acid. All right, so we have that strong absorption and the carbonyl. All right, here's our third spectrum. Again, let's just get rid of some things to make our lives easier. So we've identified these two. All right, let's label the peaks. Here you have 2,900. Here, let's make that 2,950. Maybe 2,900, and then I would say maybe like 2,890. All right, and then you really have nothing. These are sharp, intense signals. Not much else going on. You do have a signal here right around 1,500 wave numbers. So pause your video and go back to that table and see if we can identify these signals. So looking at this, again, not much going on. You should see that this is your CH absorption. All molecules have it. We've seen them in the previous spectra. And again, you have this non-distinct 1,500. I wouldn't say, all right, this is probably not a CC double bond. So in the table, it says an aromatic CC might show up over there, but not an isolated alkene. Just to refresh you, an aromatic would look something like that. So based upon the lack of an OH, an NH, and a carbonyl, and even a CC double bond, I would say that the winner would be that alkane. Oops. All right, so we've done the alcohol, the dicarboxylic acid, the alkane. Let's label our signals here. We have a signal right around, again, 2,990, and then maybe another one around 28. Now let's make that 29. So when you do this in lab, it'll be a lot easier to label the peaks. And then you have a very strong signal. The frequency of that signal is right around 1,750 wave numbers. Pause your video, go back to that table, and see if you can identify the signals. You should see that these are CHs, and here you have a signal. Particularly an ester carbonyl will show up in that range. Now, you also would have a CO bond in an ester. Now, those are a little bit harder to see. They're in that fingerprint region. And I didn't label anything here, but I would say that that's a possibility that that's a CO absorption. All right, so the only thing left that we have with the carbonyl is the ester. Now, you're not always going to have a molecule choice, but again, just because of where this hits and the fact that there's nothing else, you only have CHs, it's a good indication that that's your molecule. For a carbonyl. Okay, let's do this again. You're only going to get better at this the more we practice it. That 2990. Again, you should know now that those are CHs. And then there's really not much else. Maybe we could say this one here looks like it's right around 1600 wave numbers. Pause your video and go back to the table. So based upon the table, I'd say that 2990, these here are your CH stretches. And then finally you would have, this would be a CC double bond. You might have caught on the table as well that if you have an alkene CH, you'll get an absorption, a weak one, right in that vicinity. So the only choice that makes sense here would be this alkene. Our only molecule left is the amine. Let's see if it matches up to the spectra that's shown. An amine, the NH stretch, is weak and generally will occur around 3300. So check, we have that one. Then you have our CH stretches, and you have CHs is present. And then you have really a fingerprint region with minimal signals because most of this compound is an alkane. So our final compound is this amine, and it matches with the IR spectra. So this is what you're going to have to do. You're going to take IR spectra in lab and make sure it corresponds to the molecule that you're analyzing, and I'm going to give you IR spectra in your lecture problems.